Okay, so let's go back to our course. Okay, for those students who just sit in the class, okay, this is quite important because the university or the department does not allow the resource goes to those students who does not register for the course. So I apologize for that. It is okay for you to sit in the classroom to hear what I'm talking about, but as far as the resource is concerned, so I'm sorry for that. Okay, it's not my policy. If you want to blame someone, blame the university and the MOE. Are you recording? We're going to edit it. Okay, later. All right. Okay. Just to let you know. Okay. I'm not the one to be blamed. Okay. If you don't like it, you talk to your president. Okay. That's it. Okay. We'll close the session 5 minutes before 12. All right. Thank you. Sorry a little bit late because I got visitors. All right. And this is about everything that I want to talk about this part is a conversion. So this is what the engineer value is. Okay. You know the drill and you know how to do it in the future. Okay. You convert the gate into the schematic and schematic into the layout. And maybe you skip the step using the stick diagram, that's fine. But the final goal is the layout. All right, and this is for the layout. And this is the layout, the final layout, okay? And see, this is an actual one. It's because as we said in the stick diagram, there is no size information. But for the real layout, the size, I'm talking about the width and the length information is included in the layout. See, I'll show you why. Okay, this is a signal, X and Y. You see the shape? Okay, this is a rectangular, and this is a pattern. Okay, you have a lot of slash lines over here. And this is a contact, a big black hole. It's a square, it's not round, it's a square. Okay, so this is a metal, and this is different color, different shape, different patterns. This stands for polysilicon. It is also a conductive material, but it's not a metal. So right now we are going to couple the metal and the polysilicon. It's just like, okay, we want to go from the third floor to the second floor. So you cannot directly jump. You got to have a stair over there or elevator. So you take the stair and the elevator up and down. So the signal goes here using the hole, okay, because it is a stair. The signal goes down to the second level, the next level, which is a polysilicon over here. And you see that this is the current. So the current goes through over here. See that? This is the direction of that current. So this is the distance that the current travel. So this is the length of the transistor. And this is how the current goes. So this is the width of the current. So from this figure, you can get the exact, correct information about the size of this transistor. The length and this is the width, because you have to consider how the current is flow. So this is direction. Similarly, see that? This is one. So the signal goes over here. This means the input current goes over here. And this is the direction that it travels. And this is how big the current path is. So this is the length. This is the width. So the layout has the information of the size. But if we go back to the stick diagram, see? The length and the size are the same, and there is no contact at all. So we just show you, okay, the connection information, that's all. Different layers. Layers, the information of layers, information of connections, that's all. But as far as, as far as we are concerned, we like to know the details about everything. Okay? So this is where the connection is, how big the hole is, okay? And here we have another hole. Okay, this is a diffusion. a material is a semiconductor. So this is a connection over here, just like the one over there. So this is a transistor, and this is a transistor. Okay? And there's another one. This is another one. Okay, and we want to go couple this one to the ground. And we understand that the power and the ground is made of metal material. So it's very simple, symbol over there. But here we got to use the metal and the veil hole over here to do the short circuit connection. So this one will be mapped to that one. Okay, so this is schematic. That is a layout. Okay, as for this one, we are going to talk about it. This is called the well tap. It's called well contact. And this is a layout. Okay, so, well, don't worry about it. So you just briefly look into it. You understand there is a one-to-one mapping relationship between this figure. Okay, that is a NAND and the inverter. This is the NAND and the inverter. Now let's go over there to check it. We have two transistors. They are cascaded from the top to bottom. We have another two transistors in parallel. Is on the top over there. See? And this is the inverter. See that inverter? This is a P MOS of the inverter. This is the N MOS of the inverter. That's over here and over here. See? And this is the output from the NAND function, okay, and coupled to the inputs of the inverter function over here. So this is, come over here and make a short circuit, activate the polysilicon to drive the inverter, just like what happened here. So that's the layout. This is a schematic. So you want to learn something, this is something you want to learn. You can do the conversion from the schematic to the layout. That's what the value is. That's what your value is. Again, this is how you're going to get a job in the future. You are able to do efficient conversion of these two circuits. And even though they stands for the same. Understood? Understood. This is a very simple one, just for you to understand. Okay, and in this layout, you will learn, you will get a lot of information. All right? The size, the connections, and you see a big red rectangular. Okay, because a big rectangular, all the transistors that it encompasses, that it covers. They see this. If you don't have this red box, you cannot tell the difference of these two. Right now, because of this red box, okay, we understand. All the process engineers in the foundry understand. They are two different transistors, okay? And this red box stands for something. It stands for the area of well, a special well. It's called the unwell. So all the transistors sitting inside of the unwell red box stands for PMOS transistor. If the transistor sitting outside of the red box, it is NMOS transistor. Okay, so this is our job to tell the process engineer where I like to have my PMOS transistor and where I don't want to have my NMOS transistor. Okay, this is the usage of the red box. Okay, the rectangular. Okay, don't worry about it. Okay, we're going to talk about it more. So understand. So what do you want to learn in this course? From the gate to the schematic circuits, from the circuits to the layout. That is what we're going to talk about in this whole semester. This is the layout. Okay, so and the wafer, the die. Okay, that big round shape. It's called a wafer. It's a pizza. I always joke about the pizza, big pizza, and a very expensive pizza. And you see a lot of squares, okay, on that wafer, because that's a picture that they take after the wafer has been turned into a lot of chips, okay, before they are dissolved. So every single box stands for special design, or special design over there. So this is the map, and this wafer from the IBM, and this is called the chips over there, and this is your design, okay? And in okay, according to my experience before, in that big pizza, we select 5, maybe up to 9 dies, okay, as the testing samples on a single wafer, and to carry out the so-called W02, wafer access test, to test whether the homogeneous of this chip is okay or not, okay? But it's not important here, just for you to understand. There's wafers, and after it's die, so it's called the die, okay? All right, now we are going to show you how the chip is made. But we're going to go through this very briefly. So right now, we use the side view to look at how an inverter. This one is an inverter, it's over here, this one. So because this is too complicated, we're going to erase it. We're going to talk about this part. Only the inverter is discussed in these sections. So inverter is composed of one PMOS transistor, one almost NMOS transistor. Okay, now we gotta have an input. Of course, we have an output over here. Okay, so this is NMOS transistor. Okay, somebody call it the N device. Never mind. Okay, or this is PMOS transistor, or the P device. It's the same thing. And we want to make sure that everybody understands that. So we use a small circle on the back of this symbol. So if you see this one, it stands for the PMOS transistor. And there is no circle, it's NMOS, okay? So this is schematic, and this is a side view of the layout. So if we now, we use a knife to cut. Okay, this is a view from the top. This is a view from the top, okay? This is an NMOS transistor over there. That's a PMOS transistor on the top. Okay, this is how it looks like from the bird view. From the bird, look at from the sky. Eyes in the sky, okay? Right now, we use a knife, okay, to cut this transistor, this inverter into half. Okay, to cut it into half. Then this is NMOS, and this is called the substrate well tap. It's over here. We're going to explain it later. Okay, and this side is ground for the NMOS. And that side is short circuit to the VDD. All right, so let's go back to the side view over here. It's called the cross section. So typically, we use a P-type substrate. This is a substrate. Basically, it has very, very few positive electrical hole in this one. Okay, in this one. It's called a P substrate. And then remember the red box that we talked about, okay, to cover all the transistors, which will become the PMOS. That stands for this part. It's called the N-well. It's called the N-well. So the N transistor must be growed in a P base, P substrate. On the other hand, P transistor must be grown or made inside of an N base, N well. But because we cannot separate these two parts from different die, otherwise we don't have the integration at all. So we have to find a way to create an environment for the PMOS to be grown. So that's why we use the bombard technology to create a well. And this well is considered the N substrate for the PMOS to be made. So that's why. So we basically, N transistor, okay, N transistor will be made and or grow in a P substrate environment. And this is the other way around. P transistor shall be grown and made in an N-well development. And there are 1, 2, 3, 4, 5 different colors. This stands for 5 fundamental materials to realize the inverters in real. So this is one silicon oxide that I talked about before earlier. So this is a isolator, insulator, okay, perfect one. And N plus is the green one, and that means we have excessive electrons in this two green area. We have extra electrons. And for the PMOS, this is orange, okay. This is the other way around. We don't have excessive electrons. Instead, we have a lot of extra electron holes. Electron holes is a positive, okay, in polarity. So this is positive. And the red, okay, or pink here, these are polysilicon, okay. And the blue stripes, they're metal. It's called metal one. We have very, a lot of layers made of metals, but this is the bottom one. We call it metal one. So 1, 2, 3, 4, 5. We have 5 fundamental materials to fabricate a single simple inverters. All right, understood? So this is the one that we draw over here. So this is the side view, the cross-section view of a MOS device. And there is something very interesting. It is called the well tap. This is called. It's not in the schematic. It's not here. Okay, this one is called the well tap. Well tap, or called the well contact. Somebody called it well contact. What is this for? It does nothing. It has nothing to do with the logic, but it is matter with the physical property of the materials. Because here, if we like to turn on, when this is voltage is high, picture this. If we have high voltage over here, what are we going to do? This is high, we are going to attract, okay, all the electrons in this area, okay, to here. You understood? When we apply a very high, okay, voltage, because this is plus, we're going to attract a lot of electrons over here, and it will become a channel with a lot of a huge number of electrons over here. And then if we apply a voltage drops between these two green boxes, and these electrons will flow, okay, horizontally, either to this way or that way, okay, basically, right? So this is a problem that we have. If we apply a high voltage here, we're going to turn on the channel over here. That means that we turn on the switch. But the problem is some other areas, not in this region, okay, they just might be attracted by the high voltage over here to become drifted carriers over here. Then these drifted electrons, they are not welcome. Because if you are attracted, you should work in the channel, not just running around the campus, okay? So these extra, okay, drifted carriers, which are negative, shall be taken away. So we apply a plus area, which has a lot of electrodes over here, to what? To do the job, clean this mess. So for those, you just tell these are homeless. These homeless electrons, okay, you boys and girls have nowhere to go. This is a shelter. Come over here. I'll give you somewhere to stay. Okay, get out of the channels that we want to transmit the signal. That's the purpose of this well tap. So the well tap, okay, it does not appear in that schematic. However, it is required in the real physical implementation, because the purpose and the function of this one is to clean up all the drifted or random particle, random carriers in the substrate. Okay, similarly, we're going to have another one, because what we like to have here is electro holes. Electro holes that we have a negative over here. We're going to attract many electrons over here so that they will work together. But for those electrodes created in this part, they are not needed. So we use N+. N+ means that we have a lot of excessive electrons. We are going to combine them together. Just tell all the electron holes over there, come over here, okay? Okay, well, I'll give you some shelter, okay? And don't just running around to create a problem. So the substrate must be tied to ground and the well to the VDD. So this is metal. The reason why is that metal to lightly doped semiconductor forms a poor connection called a Schottky diode. Schottky diode, all right? So use heavily doped well and the substrate contacts. It's called a well contact or a well tap. So that is the reason why we have this. See that? Okay, this is coupled to the ground, right? What is this for? This is the purpose of the well contact. This is the purpose of that well contact. It's nothing to do with the logic. You can consider these two extra well tap. They work as janitors. They work as cleaners to clean up all the unwanted carriers. All right? Okay. All right. So this is the bird view of the design. And what stuff that IC designer delivered to the foundry? It's called a mask. It's a mask. Okay? So transitional wires, they're defined by masks. All the shapes, all the polygons that you draw in the virtuoso environment will be finally turned into masks. And the mask is not the mask that we wear, okay? It's useless, okay, to isolate us from the virus. Oh, come on, virus exists long before human arrive on the earth, okay? It's longer, and it is my belief virus will stay on the earth, okay, when all the people are gone. You know what I mean? So virus is the enemy that we are not going to we are unable to beat. The best policy for us is that we're going to live with the virus peacefully, okay? Or it's not about the chorus anyway. So the mask is the product after we draw the layout, and the layout file, GDS file, will be delivered to the foundry, and the foundry will get it. Use these layout files converted to masks. Then they will do it step by step, okay, to fabricate the chip that you like. Okay, so the layout you draw will be partitioned into different masks. Okay, for example, this is a very simple one. So right now we need 6 masks. The first one is the unwell. How many unwells we need? And then the mask for the polysilicon. And the mask for the N diffusion. Okay, this is N diffusion. And this is for the P diffusion. And where the holes are needed, it's called the contact. We also need another layer of another set of masks to define where the contact is. And the last one is a metal. So we see that we need 1, 2, 3, 4, 5, 6 sets, 6 masks to fabricate a very simple inverter. Okay, you might be curious, what is the number of masks we need to fabricate a complicated IC design? I'll give you the number. About 10 years ago, I was invited by one, one of the top IC design houses to design the buffers. Buffer is a simple one, okay, which are the paths around the chip. According to what they say to me, okay, for a very simple point 18 design, they need 33 masks. Okay, each mask costs them around 3,000 US dollars. Each mask, all right, okay, it's very expensive. Anyway, I just to let you know, this is just example, just an example of the textbook, okay? At least we need six masks to develop the inverter. And fabrication, all right, and this is the picture in the foundry house. So if you were an IC designer, you never worry about to dress like that, okay? Okay, those dress are needed when you work in this kind of clean room, dressed like an astronaut, right? Astronauts. Well, I'll tell you the sad story about this kind of thing. When you wear like this, you cannot go to toilet room, you know, at you want. You have to take the suit off, and then they go to the toilet room, and then come back, you have to suit up again. So a lot of students that I know, a lot of process engineers I know, they wear diapers when they go to this kind of room. Because it's so, so much trouble to take it on and off after you suit up. And so that they have all kinds of disease about for this kind of thing. For example, the bladder, your bladder. Okay, your bladder must be very strong to hold everything in. Or you gotta have very strong bladder, strong appendixes, so that you will not suffer. So, and when you read the report that TSMC and the UMC give a lot of a bonus or a very high salary, okay, don't be jealous, because everything has its price, nothing's free. Okay, I'll give you an example, because I might be the poorest guy in my class, because all of my, most of my college classmates, they go to industry. They earn a lot of money, okay? But, and then they retire very early. Some of them retired before 55. Right now I'm 61, I'm still teaching in the college. But the thing is, as far as I know, a lot of them have health problem, okay? Some of them, okay, almost die because of heart stroke or brain stroke, okay, because of high pressure environment. And some of them have diabetes problem, okay, because they have to drink a lot and they have to eat a lot because under the pressure and the stress, all right, okay? Well, the money is good, but I will never trade my health with money, okay? It depends on how you look at it. And some of my college classmates, they are really rich. For example, the #2 employee of Broadcom, you checked out Broadcom, one of the largest IT design houses in the world. Okay, #2 is my #2 was my college classmate. About 30 years ago, when we have a college class reunion in San Francisco, well, we were told that he already have like a 50 million US dollars back then. 50 million US dollars 30 years ago. Check that the number. Okay, that means that it could be 5 billion right now. And then, well, the money is good, but if you cannot enjoy the money that you earn, that's pretty sad. Okay, depends on how you think. All right, this is, well, I consider this a trade-off between the income and the life quality. It depends on how you think. Well, and a lot of my college classmates, they have a liver problem. Liver problem. We'll talk about that later, okay? I don't want to scare you off. okay? So this is the fabrication steps. We're going to go through this very quickly because we are not a process and engineering course. Okay, just to let you know, show you some figures how it is done. So this is a fabrication step. Very easy. Just look at the pictures. You understand what happened in the foundry. Okay, this is an example to fabricate an inverter, right, from the bottom. So the first one is that, okay, the covered wafer with protective layer of silicon oxide, and remove layer where the N-well should be built, because we need N-well over there. Then implement and diffuse undopants. Okay, undopants mean the material, okay, with excess electrons into explosive water at the strip of the silicon oxide. So I show you the pictures very quickly, then you understand what happened. See, this is step number 1. To grow the silicon oxide is called oxidation. Well, and the temperature is 900 to 1200 degree of Celsius using the spray of water or high density oxygen in the furnace. Then a single layer will be grown on top of the substrate. Then on top of the substrate, we deposit with a material which is called a photoresistor. Photoresistor material are very light sensitive, organic polymer. So the material engineer is important in that business. Then it will soften where it is the part is exposed to light. So we can dig a hole like this. Dig a hole like this. This is a way that we like. Okay, so that is a top view, bird view, and this is a side view of what happened. Okay, and the next step. Okay, next step, we etch. We etch the oxide with a very nasty stuff. It's called the hydrofluoric acid. It's a chemical substance, and it could kill. It could kill. So it sips through the skin and its bones, very nasty. So if a single drop on your skin, then it's better for you to run to the hospital. Okay, it will go all the way down through your skin and your bone, okay, and you will cry like a baby. Okay, it's very nasty. That's why you got to wear a lot of protection over there, okay, to prevent the bad things happen to you, okay. So then this kind of stuff attacks oxide where resistor has been exposed. So up to now, you understand that the process of semiconductor, okay, needs a lot of things. High precision masks, okay, high purity of materials, right? So it's a very complicated industry, engineering. So Maurice Strong joked about one thing, and I think he was pretty serious. Sometimes I admire this kind of this gentleman. He emphasized one thing, okay. Even though the American government announced they want to spend $40 billion to duplicate the foundry in Arizona, where where I'm invited to visit, there is no way for Americans to duplicate that kind of a precision in that plant. Why? I'll tell you why. Okay, because Taiwan, as I said, Taiwan is the only country in the world that we have 80 high-quality process engineers, and they work 24 hours around the clock to maintain the quality of that semiconductor quality. That means the TSMC. And for those Americans or those European guys, okay, as soon as 5 o'clock is alarmed, they want to get off. Okay, they never receive. They want to take a phone call in the middle of the night. Okay, they want to take a break in the weekends. So how the hell you can have that kind of quality of a service? It's impossible. Only in Taiwan, because all the engineers, okay, they work their butt off to get paid. That's why. That's why they need a lot of young talent, the fresh legs like you guys go over there to sacrifice your youth and to trade money. You understand? Is that cruel? No, not at all. It's up your decision. And because I know a lot of kids a lot of kids are coming from a poor family, and they desperately need money to change their life of their family. So it's a good thing. But in the end, you gotta understand that what you pay to get that kind of money. Okay, and that's why. All right. So I'm not worried about any other country can duplicate whatever Taiwan has achieved. That's impossible. Okay, even India, I have received the invitation from India, my friends. They want me to go over there to be consultant to set up their supply chain. I was joking. Well, it's not a matter of money. It's about how much time you want to spend and how the education system will be in your country. You see my point? Okay. If you don't change that kind of thing first, you will never have the same supply chain in Taiwan. That's impossible. Okay, China wanted to do that about 20 years ago. Now they fail. They fail. It's impossible. Because the Chinese, is there any Chinese over here? No, I don't, if they're recording, okay. I don't want to say the bad things. But sometimes I have to do the transit in Hong Kong or Macau. I don't want to be taken under custody and then sent to Xinjiang to be the cotton pick. Anyway, skip that part. I'll just let you know that, okay, we need a lot of chemicals, high quality chemical, and high precision mask engineering. All right, so this is etching. And then we do the strip the photoresist again. All right, we just resist the part. We use a mixture of acids called the binary etch. Okay. Then unwell is made by what? By diffusion or ion implementation. Diffusion, this is an old-fashioned way. That means the wafer will be placed in the oven, okay, a furnace with arsenic gas. Then after a while, the gas is spread over this part because we have a window over there, okay, and then the N plus material will be doped into this region. Okay, this arsenic items diffused into this part. But this kind of process being discarded because it's too slow and it's not homogeneous enough. So recently, every foundry uses ion implementation. You use a laser gun, something like that, okay, to blast the wafer with a beam of the arsenic ions over here. And these ions will be blocked by the silicon dioxide. So the quality is better, okay. I'm not talking about the time is shorter. I'm also talking about the quality, homogeneous. Homogeneous is better. All right, then split them off. Then we're going to get this part, get something like this. This is a bare wafer. Now unwell is well done over there. All right. So similar step will be taken. Okay. We just coat something and then do the etching. Okay, and then deposit something. The second one is called polysilicon. Polysilicon is a thin layer of gay oxide, and it's very thin. Okay, 20 angstrom, 6 to 7 atomic layers. And this special process is called a CVD, chemical vapor deposition. Okay, and this wafer will be placed in the furnace with a saline gas. Okay, saline gas. See, another chemical substance. So a lot of crystal will grow on the top, and this is a very good conductor, It's a good one. So we use that to serve as the gate controller. This is a mask. Okay, the patterns that we use to create the gate, And this process is called a lithography. And then we go through the similar steps again repeatedly And this kind of process is called a self-aligned process. This is where the difficult part is. TSMC right now is the best in the world. They can do the alignment really good. And this is why the Samsung or Intel or those companies in China, they right now cannot catch up with the TSMC, because when it comes to very, very thin, okay, advanced process like the 1 nanometer, 3 nanometers, okay, it's up to how you control the machine really good. So these are oxide and masking. You expose where the N+ dopants, it should be diffused and implant. Okay, right, this is how it's done. All right, now we need the N diffusion to grow the N transistor. Okay, so we gotta punch 2 holes over there, and then bombard with the with the material. We need a well tap over here. Well tap over here. It's a self-aligned process. Okay, polysilicon is better than metal for self-aligned gates because it does not melt during the later process. So this is what happened. Okay, what we get after N diffusion is done. So this is a diffusion. We got 2 green boxes to work as an N transistor. Another one green box to serve as a well tap, okay, in the N well. Okay, this is called diffusion. And then N diffusion is gone. Then we repeat the same process for PMOS device. That is called the P diffusion. Okay, similar set of steps from P plus diffusion. Okay, so that we create a pair of P plus boxes over here. That is the P device, and we'll tap over here. Then the last one is a metal, I think. Oh, this is a hole. We got to create holes for the signal to travel up and down, not just horizontally. So we need to wire together the devices. So we cover the chip with thick field oxides, and we etch those oxides where the contact cuts are needed. Basically, you can consider we are building the stairs or elevators for the signals to travel up and down. Okay, otherwise, different layers, they cannot talk to each other. Okay, this is the contacts. And the last one is the metallization. The metal is on the top. Okay, metal on the top. So the metal pattern, we own the spot machine using okay, before I forget, all the metal wires that we use aluminum, not gold, not silver, not copper. Okay, I understand the conductivity of a silver, gold, or copper is much better than aluminum, but the problem is aluminum is very cheap. Is it very cheap? It's affordable, so that's why. And gold it's not possible because it's too expensive. Okay, the same as a silver, and the copper is too heavy. If you cover the semiconductor with a copper, after a while, those copper elements will go down to the bottom and destroy everything because it's too heavy. So the metal material basically is alumina. Okay, it's light, it's cheap, and it's fast. Okay, now this is inverter layout. So it is how it looks like after the fabrication. And there are something new to you over here. You'll see something very interesting. You'll see a number. It's number over here, number over there. These numbers, they stand for something meaningful. Okay, nothing meaningful. What is that? Okay, let me tell you what. So after the fabrication, we see, after the design, we see that, oh, okay, we have, this is well contact, and we have a polysilicon over there. This is metal. We have a diffusion on top. This is a PMOS device. And this is a NMOS device over here, over there. Okay, we have a ground and a well tap. Everything looks good, except one thing. How come these 2 transistors, they are not the same size? They are not the same size. Okay, see this one? The current or the signal travel like this, okay? We're coming over here, go 3 over here, right? Okay, go this way. So this is basically where the signal goes, okay, and getting out of there. So what you see is that this is where the signal travels. So this is the length. This is the length, and this is the width. And the same thing over here. This is the length that the signal travels, and this is the width. So apparently, these two transistors, they have the same length, but different width. Why is that? See, everybody has the same length because we use the same strip of polysilicon. So basically, we understand that the signal, no matter it travels on the top or the bottom, they go through the same length. But how come the different ways? Okay, there is a trick behind this one. So this stands for the length. Length 2. What does the 2 mean? Why not 3? Why not 1? Because there is a story behind that. Remember, at the beginning of this lecture, I mentioned a book written by Professor Milton and Conway. Okay, they define the minima size of a certain process. Okay, is the width of the transistor, and it's called lambda, number of lambda. How many lambdas? So in Milton and Conway's book, they are the first group. They are the first one in the world to define. Okay, we use a lambda as a unit to denote, okay, how big or the size of the transistor. So 2 lambda stands a minimum size of this process. So 2 lambda over there. And then this is the length, and this is 4 lambda stands for the width. So the slash, right-hand side of the slash stands for the width. Left-hand side stands for the length. Okay, it's called the 1 unit. And this is a very, very old process, 0.6 micron. Okay, I'll give you the number. Okay, when I was a student, I used a process 2.0 micron. 2.0. Okay, it's a, if you compare with a size, okay, it's just like a truck. It's like the size of a truck. And right now, the process that you use is the size of a bicycle. Okay, the truck. I designed the truck. I use a 2.0. And in this textbook, it's 0.6. Anyway, so this is a feature. So the minimum size is 0.6, 0.0 length. So the lambda is 0.3. Okay, the smallest, the minimum size is defined as 2 times lambda. So the lambda for that process is 0.3. Never mind. Okay, just to let you know. So since the length is the same, so we just take them away, and we just leave the ratio of these two processes. These 2 transistors, 1 versus 2, because on the top is 8 lambda, and it's 4 lambda. It's 1 versus 2. And you might be curious why the one on the top is bigger or wider than the one in the bottom. Why is that? It's really easy. Okay, what is the carrier for the signal to be used on the top? For the PMOS device, you use the holes, right? These are your electro holes. And for the NMOS device, you use the electrons. Use the electrons. Somebody's taking a picture of me. I feel like I'm an idol already. Or that some guy sent by the CIA or FBI. They might be suspicious. I talk about a lot of confidential stuff. This is nothing. Okay, holes. Which one is faster? This one is fast. This is a fast guy. And this guy is slower. Okay? So in order to equalize the delay, this is for the charge, right? And this is for the discharge. Because this is one, when it is on, we are going to send the current from the top to the middle. This is for the load. Oh, this is the load. Okay, when this one is on, this is off. We're going to discharge everything on this capacitor on the load. We're going to discharge it. Okay, if you want to equalize the delay of these two operations, one is charging, the other one is discharging. You got to think of something about that. Because this guy is slower. So you got to increase the size of this one so that we can have a bigger current. Because the speed of the charging discharging is proportional to the magnitude of a current. Understood? The speed is proportional to the current. If you have a bigger current, we can charge this faster, right? Okay? If you want to charge it slower, we can use a small current. So the current, okay, is made of a hose. It is slower. So that's why we have to magnify the size of the PMOS transistors so that the charging time will be equal to the discharging time given by a MOS device. That is why we need a wider device, okay, a wider device on the top close to the power supply. Okay, and then we need a smaller size, a thinner transistor close to the ground. We'll explain it later, just to let you know, because the size does matter. Remember the movie Godzilla? Godzilla. Okay, size does matter. Yes, size does matter in IC design. So very informative. From this figure, this is a layout, we have the picture about the size of different transistors. And why the size is different? Because there is a demand behind that. It is called the equalization of speed, charging and discharging speed, or charging and discharging delay. We want to do that. Understood? Okay, so the inverter design, you might be curious why the size is different. That is the reason why. Okay, we're going to show you a video, and this is a lovely one. This is, I got to give the credit to this university. It's not in our university. to these guys who made this film. Okay, now let's talk about the money. Okay, money is that everybody loves, all right? Well, the economy is a driving force of everything in the society. I'll give you some rough picture about everything in this business, okay? So the first term that you should learn is called the NRE. NRE is, the name of the NRE is a non-recurring engineering cost. It's called NRE cost. What does that mean? That means the cost that you will spend no matter how big the project is, the NRE. For example, I'll give you some example, okay? You will stay in the house, in your home, in your house, or in the house that where you stay with your girlfriends or boyfriends, that's fine. Okay, you gotta pay something every month. For example, electricity bill, the water, okay, maybe rent. Okay, this is just a DC value. Okay, you have to pay anyway. Okay, no matter you stay in that room or not, you got to pay that. Okay, so it's independent of the sales volume. It's nothing to do with one chip you sell or a 1 million chip you sell. Okay, it's a basic expense you have to pay. It's called NRE. And this is also stands for the effort in time, okay, and the manpower you have to spend for the special project. Okay, the NRE will be the same even if you design an inverter. It's the same for designing an inverter. The microprocessor is the same. Okay, it's the effort in time because you need 100 engineers to do the inverter design. You need 100 engineers to carry out the CPU design. What the hell is that? What the hell is that? They were partying in the upper floor. All right, and then R&D cost, manufacturing equipment. You need equipment and instrument. Okay, you need steps to do the marketing and the sales. Okay, and then you need to pay the rent, the house, and the utility, everything. It's called NRE. Okay, it's a fixed amount of expense you have to spend. And another part of the cost is the variable cost. This part of the cost is highly related to how much stuff you sell, or how much your product is. So the cost per IC is equal to the variable cost per IC and the fixed cost over the volume. So the bigger the volume that you sell, this part will go down. See? Understood? If you sell 1 million chips, okay, and this fixed cost will be divided and will be spread over the 1 million. So the overhead cost will become small. If you only sell one chip, then you have to spend $1 million for that part. That's unacceptable. That is why the volume is important. So that is why a lot of IC design houses, they like to sell the design and sell the ICs that are hard and popular on the market. Okay? Because the volume will be big. And this is a variable cost per IC. So let's check the numbers because we all like numbers. Okay, the cost of IC. Okay, the cost of IC. I don't have a laser pointer. These kids, they don't prepare for that for me. Never mind. The cost of IC, okay, the denominator is that the cost of the die, the wafer, and the testing money, the cost of testing, then cost of packaging and the final test. So you got to pay the money for the die, testing, packaging, and test again, divided by the number given by the wafer, single wafer, And what is the percentage of the good dies? It's called the yield. Bad dies will be drained in the toilet, okay, will be dumped in the garbage can. They don't be needed. So this is the cost of IC. And as for the cost of a die divided by the cost of wafer divided by the yield rate and the dies per wafer. So that is the reason why all the foundries, they want to grow a bigger pizza. Because when the pizza is bigger, okay, and we can deliver more dies on a single wafer. So the cost of that will go down. That is why it's the competitiveness of TSMC is so strong, because they're really good. They're really good. And this is the equation for that. I don't know how the equation it was calculated. Basically, this is an empirical conclusion for that. Never mind, we just take advantage of this equation. Basically, you can understand that A is the area, D is the diameter of the pizza, and the yield, okay, will look like this way. It's a very interesting equation. Okay, we don't know what that is, but never mind, we just took it, okay, and use it. So this is a defect density, okay, 0.3 to 1.3 per square centimeter. Alpha is a fixed number, okay, it's a 4.0. Okay, we take all these equations and we abuse them to find out interesting thing. Give the numbers. When you talk about numbers, you understand. So, okay, so right now, if you are a lousy designer, okay, we have two examples. You're a lousy designer. You need 1 centimeter square to realize that certain function. And the wafer size, the diameter is 30. And the D0 is 0.7. And the cost of wafer is 1.5 thousand US dollars. This is normal price. Don't be surprised. Then we take the equations and then do the math. We find out that we can only deliver 660 dies on the wafer, and the yield is 0.57. That's really bad. 4 out of 10 chips are bad. Okay, the cost of a die will become $4 per die. $4. Are you joking? We are not talking about a CPU. We're talking about a normal design. $4 US. That's not acceptable, because it divided wafer price, and this is a number, okay, per die, and this is the yield. That's very expensive. Okay, check this out. Now this company hired a very good designer. Okay. Now he can carry out the design with the area of 2.5 millimeter times 2.5 millimeter. Okay, the size has become like 1/8 of the original design. Everything else stays the same. The wafer size, the D0, the cost of everything the same. So check this one. The dies per wafer will be over 10,000. Wow. Check this out, 10,000. The one that we showed that 660. Then the yield will be close to what? Almost 100%. It's 96. Okay, the bigger the die, okay, the higher chance that the chip will fail. So make it smaller, you have a higher chance that the die is good. Then the cost of everything will be what? 0.15 US dollars. Very competitive price. Very, very attractive. So everybody loves it. Your boss, your customers, your clients, they all love it. That is what the IC design value is. Okay, bring down the cost, make it very competitive in the market. So cost of fabrication, this is not affordable. I just let you know how lucky you are. Okay, just know how lucky you are. Okay, because only in the university, Taiwan University, you have the luxury and the privilege to tape out the chip without paying a cent, without paying a single penny. Because the government of the school, okay, pay that for you. If you want to go to the TSMC, you knock the door, say, Maurice Strong, I want to tape out a chip. You got to make sure that you have a deep enough pocket to do that. Check this one. Okay, the fabrication, maybe 3 billion. We're not talking about ID dollars. We're talking about US dollars. All right. So the production line is one city block, so it demands a larger area. Okay, you must be aware that TSMC make an announcement that they want to build a plant in Kaohsiung. Is that right? You heard that news, right? Okay, so that gave a boost about the real estate market. But recently, they announced that they want to hold that plant for a while. Then the real estate market goes down. Okay, like a roller coaster. All right, and we need a lot of manpower. All right, and then the profitable period is the first 18 months to 24 months. So the NRE, this is a reasonable price. Okay, for the very legacy process, 50K. Okay, now the process that you use in this course, that's point 18, 200K US dollars. Okay, you don't have to pay a penny. You don't have to pay a penny. So why don't you take the course? Okay, take the course, you can enjoy the benefit. Okay, challenge of everything. So challenge of VLSI design in the future. So I myself, even though I'll be retired in 5 years, then future is yours. It is my belief that in the next 3 decades to come, 30 years, VLSI is still the hottest, one of the hottest area in the world, because everybody likes to have what? Okay, cheaper products, smaller products, okay, and convenient products, and only ICs, okay, can achieve this kind of performance. Okay, nothing else, all right? And of course, everybody loves it. That means the competitive is very strong. You got to be aware of that. So what is the future challenge of IC design, or VLSI design? Apparently, we have these 3. The first one is interconnection. Interconnection means that because we like to have a massive computing power, that means we are going to have a lot of process units on a silicon die. So the interconnection is a problem. So because we have millions of processors on a single die, so the while delay, will become longer and longer. So the while lengths become longer and longer, that we're going to create a problem of delays. So in the future, what we can see is that the while delay will be bigger than the gate delay. Because in this kind of design, usually you'll be told, you are told when you are in the first year, your professor, for example, me, I will tell you that we only count the gate delay. Count the gate delay over here. So here you see, oh, okay, we have 3 inverter delays. But in the future, the gate delay is nothing. The problem is here. This will be the problem. The while delay. The while delay will become a big problem. The longer the while, and the switching speed of the devices will become faster and faster. But the problem is that the delay over the while become a big problem. The second thing is power. Power is the boundary of a human being, because we don't have unlimited power, right? Okay, for Taiwan, like they're recording, right? Taiwan's biggest problem is the power, because we don't have enough energy. 99.9% of Taiwan's energy, okay, is imported. Okay, that's a problem. We use the gas, we use the oil, we use the natural gas. Okay, they are all imported. Okay, and of course the government talking about the green power, which are major from the solar power and windmill power, but they are only a small amount of that. It's too expensive. It's unaffordable. It's not a large enough. And the nuclear power, Nuclear is considered, right now, is considered one of the green powers because it creates nothing about the carbon dioxide, okay, that will help to reduce the air pollution. Today, air pollution is really bad. But the problem is the nuclear waste is something that we cannot deal with. So far, we don't have any solution for that. So that means that the consequence is bad because we enjoy the nuclear power, but the problem is our children is going to suffer because they have to deal with the nuclear waste. So that's a that's a trade-off, all right? So Taiwan's problem, I would say that Taiwan's boundary in the future is how to deal with the power problem, okay? So anyway, let's go back to what we were supposed to talk about in the course. So the power is the biggest problem in the future because the die becomes smaller and smaller. If you don't reduce the power dissipation problem, then the chip will become too hot to deal with, and it will melt down, malfunction. So picture this: when your notebook, you have notebook, a cell phone, when you touch it, you feel that the battery getting hotter and hotter. What are you going to do? Okay, you're going to replace the battery, right? Because you don't want to fry your cell phone. You don't fry your notebook or pad. That's why. So the hotspot problem is one to be dealt with. And the last one is the conflicting constraints. Constraints, that means we have a lot of demands, but these demands, they might be contradictory to each other. Okay, we like to have a lower price, but the thing is, in the meantime, we like to have higher performance, but basically they are contradictory. It's impossible to be satisfied simultaneously. At the same time, it's impossible. So low cost versus high performance is something that we are not so easy to achieve. So, and the last one is the system complexity. AI is coming, as I said at the beginning. So AI is the biggest problem. AI needs a lot of computing power, but of course, it will consume a lot of power, okay? Then how to deal with the heat dissipation. Then we are not talking about the ASIC problem because right now a lot of students, some students already start to use the GPT to make a composition, okay? But I tried that thing, okay? It does not work too well. But I think it will be improved very soon. It will be improved very soon, but that's in the future. So basically, when the system becomes bigger and bigger, we need to find a way to do that. It's divide and conquer. And then solve the problem one step at a time. Okay, so the TS are here. So let me stop here. We are going to continue this part. Okay. So the homework is this week. You don't need to have. I give the homework to the TAs, so it's better for me to next week it's supposed to be the holiday, so basically you have 2 weeks to do this homework. It's very easy. All right, so my assumption is that you are Windows-based addictor, okay? Addictor. You are addicted to the Windows systems. But for the IC design, you got to use a different system. It's called a Unix base or Linux base. So if you are not familiar with that, that's fine. Okay. So the TAs will give you a session this Wednesday, 6 to 7 maybe. Okay, here in this classroom, to tell you how to use this tool. It's Cadence tools. The tool that we are going to use for the whole semester. You are going to design your schematics and your layouts, this kind of thing. On the system, the system is based on Unix and Linux. So this is one. So in this week, your TAs will show you how to log in a workstation. If you don't have the account, okay, get one. Okay. Of course, the pre-requirement is that you have to register for the course. Because you don't pay for the class, you are not supposed to share the resources given by the department, which are supposed to given to those students who register and pay for the course. So, and then you're going to create your working directory, and then start a Cadence software, all right? And they'll tell you how to do that, and then how to open the different different views of a design. And then because students like to work from home, okay, because you want to get up in the morning, suddenly you have a crazy idea, I want to build a CPU. You want to do it from your house, your dormitory, that's fine. So you got to do it remote login, because the server and the workstation sitting in the department domain. So you got to do the remote login from your house to do that. And then, of course, everybody run into a lot of problems. So how to do the troubleshooting? And the TAs will tell you how to do that. Okay, don't just close the window because the process stays in the system and it won't go away. You must learn an efficient way to kill the process that you don't need. Okay, and my TAs will tell you how to do that. And if you want to do the design in the department, that's fine. And they will show where the workstation is. I think it's the 6th floor, is that right? Okay, go over there and do it on-site, that's fine. And the technology file, in this course, we are free to use the UMC 18, and they'll give you a technology file, and you can you can play around with that. All right, and maybe your TA will tell you what to do. And I told them to prepare the menu for you to download it. Right? Is that right? It's a Chinese version, English version. Chinese version, so that will save your ass. Okay, sorry, bad words. So that's why. Okay, and what to hand in 2 weeks from now. So make sure that I want to make sure that you understand how to play around this stuff. So I need you to hand in hard copies of 3 things. Okay, screen dump your own account. Screen dump your own account. Okay, screen dump your Cadence command window. Well, that means you know how to start the Cadence. And screen dump your working directory that you created. That's all. That's all you need. All right, very easy peasy. Nobody gets hurt. All right? So any question? Otherwise, we'll stop here. I will see you 2 weeks from now. Next week is a holiday, right? And now I'll be in Manila. All right, okay, go find your lunch. Okay, we stop here.